Welcome to my videos on deriving a Poisson distribution. So in the previous 4 videos, which is video number 2 to number 5, we derived the property mass function for Poisson distribution either from the Poisson postulate or as the limit of binomial distributions. So now we treat Poisson random variable x as the number of arrivals in a fixed time period from 0 to t, where the time between two consecutive arrivals follow exponential distributions. So that is, this is 0 and this is t, and we have this nt here. So nt will be the number of arrivals in this time period, and this is the first arrival time, s1, and this one is the second arrival time, s2, and da da da. And you know that the time between two consecutive arrivals here. So now we are assuming that this distribution is exponential distribution. So under this condition, we will derive that the nt now is a Poisson random variable. Okay, so the picture for this setting again is like this: 0, and then this is t, and then we have t1 here. So t1 is the time for first arrival, and the t2 maybe is here. So t2 is the time between the first arrival and also the second arrival, etc., etc. So assuming that we call this one as the so-called the inter arrival times, t1, t2, da da da. And we are assuming that these ti's or IID follow the exponential distribution and with the property density function, which is given here. So you can see that we can define the time of the nth arrival. So Sn is the time of nth arrival. So for example, the S0 is just equal to 0, and S1 is simply equal to T1, and S2 will be equal to T1 and then plus T2, and then da da da. So in general, Xn is equal to the sum of Tj when j running from 1 to n. And nt and then will be the number of arrivals Sn's in the time period from 0 to t. So nt is here. So you can see that the nt actually satisfied the condition that Sn will be less than or equal to t, and then we want to find out the maximum value of n satisfy this condition. Or we can say that this nt will be equal to the integral value n, so that the Sn will be less than or equal to t, but next Sn plus 1 will be strictly larger than t. And we are going to show that this nt will follow the Poisson distribution. So here's one example. Just show you the data structure. So here, suppose that we have an ID sample of t, and the first value is equal to 0.994, so that's t1. And the t2 is 0.992, so that's t2. And then t3 is equal to 0.423, and then this is the t4, which is 0.124. 149. And then we have like a T5 and da da da. Okay, and then you can see that S1 is simply equal to T1. So it reaches this value. And S2 is equal to the T1 and then plus T1 and then plus T2. So the sum of these two values so give you 1.986. And similarly, the S3 is equal to the sum of this, this, and this. And then this S4 will be sum of these four numbers. And then S5 will be equal to sum of these 5 numbers. And you can see that now we are focusing on the value of t is equal to 3.2. So we find out that the S1, S2, S3, and S4 are all less than or equal to 3.2, but S5 will be larger than 3.2. So this means that the nt, which is the n of 3.2, is equal to 4. So here's the theorem 3. So the nt defined in the equation number 8, so which is this equation here, follows the Poisson distribution and with mean value which is equal to lambda times t. So we are trying to establish this property mass function. So again, we use the method of we want to use the moment generating function to establish this equation. So the moment generating function for each ti, for each tj is just exponential distribution. So it's given by this equation. So we just get this result is equal to 1 over 1 minus y over lambda. And because this Sn is equal to the sum of T1, T2, T3 up to Tn, which is IID, so we know that the moment generating function for Xn is equal to the moment generating function for each Tj and then to the power of n. So which is equal to this function. So actually, if we check this property mass function, the moment generating function, we know that this moment generating function actually is the moment generating function for gamma distribution, and with the alpha value equal to n, also this beta value equal to lambda. So this implies that the Sn actually follow the gamma distribution. Therefore, we can check the table of any statistical textbook and then find out what's the property density function for gamma distribution, which is given in this form. So now we compute the property mass function for that nt equal to n. So this is equal to the chance that Sn less than or equal to t, but is strictly less than S sub n plus 1. So this is the same as the so we can calculate this property conditionally. So by fixing value Sn equal to S, and then this t should be bigger than this S, and then t sub n plus 1 will be bigger than t and then minus S. Okay, so this is equal to this integration then. And we can fairly easy to find out the property that exponential distribution is larger than t minus S, so which is given by this value here. And then also plug in the property density function for Sn, which is here. So the critical point now is that the e to the negative lambda s will cancel with this e to the negative lambda and then times this negative s. So perfectly. So now we can see that we can put this e to the negative lambda t out, which is here, and then lambda n here, and then n-1 factorial here, and the remaining term will be the integration from 0 to t, and then s to the power of n-1, and then ds. So this is a simple polynomial, so it's very easy to get this integration out. So finish this calculation, we know that the property that nt equal to n is equal to e to the negative lambda t, and then lambda t to the power of n, and then over n factorial, which is exactly what we need. So what we have done so far in the videos number 2 to number 6. So we see that a Poisson random variable can arrive in several ways. The first case is from a Poisson process, and in this case we present 3 proofs for the Poisson property mass function. And the second case is that Poisson random variable can be treated as the limit case of a binomial distribution. So where the number of trials is large, and then also the success probability is small, and then their product remained constant. So that is the binomial n, and then lambda over n. So you can see this lambda times n times lambda over n is just equal to lambda. So here you can see this n is large, and then lambda over n is small, and also the product between n, also this lambda over n is just equal to lambda, so it's constant. So the third way is to using a sequence of ID exponential inter-arrival times to define the Poisson random variable. So in this case, we also present one proof. So from this discussion, we can see that the moment random function actually is a fairly effective tool that applies to all cases. And also, this moment random function actually is accessible to the undergraduate student, because we do not need to use the differential equation. Also, we do not need to use the complex function. In the next video, we will discuss the case of non-homogeneous Poisson process. So that will be the last videos in the sequence of this about Poisson distribution. So in the non-homogeneous Poisson process, the rate lambda is no longer constant, but depends on the time t. So which means that this lambda t is a function of t, and the goal still is to derive the property mass function of nt. Thank you for watching.